All right, hello. My name is Hunter Holland, and this is my and Amanda's project, our first lab for astrostatistics on applying the linear least squares algorithm to a set of data to determine an estimation for the age of the universe. Now, observations of our universe have shown that there is a strong relationship between how fast a galaxy is receding from us and how far away it is. The dataset we were given for this project is a set of galaxies, their velocities and their distances, and here's a plot of that. And we could use this information to calculate the age of the universe by using the very simple equation time equals distance over velocity. So given a plot of the distances as a function of velocity, as we have here, all we need really is a good approximation of the slope in order to get a good approximation for the age of the universe. We could use a package called polyfit from NumPy to actually fit a best fit line to this data. And in doing so, this is what you get. Behind the scenes, what's actually going on is a solving of this equation for beta. We have our velocity vector and we have our distance vector, and all that's going on is just the package is solving this equation for beta, where beta is a 2-vector of both the slope of the line and its y-intercept. We could also do this on our own by implementing a version of the normal equation. That's actually what's going on behind the scenes of polyfit, and so when you do that, we would expect for both beta values from both calculations to be the same, and that is in fact what you find. These are the values that you get, and so the line is just the same, so we could actually call this line both the unweighted polyfit and the normal equation. But this isn't the whole story, because you can see these data points have error regions, and we could use these error regions to actually perform a weighted polyfit calculation to give us a better fit line that takes into account the variation in the errors. And so in doing so, this is the line you get. We could ask the polyfit algorithm to output the covariance matrix of this data set. And we need this matrix to actually calculate the error bars on our approximation for the age of the universe itself. What it boils down to is the very simple equation, age of the universe is equal to the gradient of this best fit line plus or minus the square root of the variance on that gradient. So when you do the calculation and convert to the proper units, this is what you get. Age of the universe is about 14.5 billion years, give or take a quarter billion years. But this likely isn't correct. In fact, it almost certainly is wrong. And we could shed some light on why by thinking about the fact that not only do we have a set of data points, but those data points aren't for sure known to be the true values. They have error regions around them. We could recognize that these data points are really just the mean of their error region. So we could simulate statistically equivalent sets of data by randomly choosing new data points from within these data regions. And we could do this over and over and over again to sort of what's called bootstrap a collection of regression lines. So this is actually a plot of having chosen random points from within these data regions and applying a polyfit regression algorithm to each of those set of data points, plotting the lines that come out of it. So they all have varying slopes, they all have varying y-intercepts, and this is what we could expect to be sort of the spread of possible values of the slope of the age of the universe. And we could visualize this distribution of these slopes, this distribution of the possible values of the age of the universe, as a histogram. And this distribution has the same mean, or perhaps better put, the mean of this distribution is just the slope of the best fit line for the true data points themselves. And this is a helpful thing to visualize. You know, if you think about it, the data that we have, by nature of the fact that it has error bars, is not necessarily a set in stone correct interpretation of what the universe actually looks like. So by visualizing this distribution, we could get perhaps a more holistic sense of what exactly is going on. Without focusing exactly on this is the correct slope, we could understand that there's a distribution of possible slopes. There's a distribution of possible values to the age of the universe. And we need to keep those in mind before we make any broad statements about this is in fact the age of the universe, because it isn't. We don't know for sure based on the data that we have in this project. To pull a little bit more on this thread of uncertainty that we've been working with, we could find another way to change our estimate for the age of the universe given the same data. We could slice our data up into chunks, use the polyfit algorithm to determine a best fit slope for each of those chunks, and then we can compare each of those values to the value that we got when we use the entire data set. And in doing that, we could actually see the relative effects of certain portions of the data set on the final approximation that we get out the other side. And the way that we chose to do this was by splitting the data up into 2 chunks. And we performed the same weighted polyfit analysis as we did a couple slides ago to each of them. And in doing so, you get a covariance matrix with its own set of values, and from that, you use the equation to calculate the age with an error region. And then we could do the same thing with the galaxies that are farther away than 300 megaparsecs. And you get another covariance matrix with another set of values. They're wildly different from each other. We could compare both of these approximations to the original approximation we got using the entire data set, and we could see something that might make a bit of sense. That original approximation is almost identical to the approximation you get from just using the closer galaxies, and it varies wildly from the approximation you get from the farther away galaxies. So this shows that the closer galaxies actually have a much higher weight on our true approximation with the entire data set, and that comes down solely to the fact that their variances are much lower. They give us a much narrower range of possible values for the slope. And because of this, they actually end up being a much better predictor for the data set as a whole, for the gradient of that data set, and thus for our true approximation for the age of the universe. Thus concludes this presentation. Thank you so much for your attention, and I hope you have a wonderful day.